friends, welcome back to my channel. This is Chandu Prashant. Today we are going to discuss about one of the interesting topic. So that is 3D transistors for a future generation integrated circuits. So it is one of the interesting topic in VLSI. So let's discuss further. So scaling to the end of the roadmap. So these are the various kinds of process technologies I had mentioned here. So 32 nanometers, 22 nanometers and beyond 10 nanometers. So in this particular topic we are going to mostly concentrate on 3D transistors. So what are the uses of 3D transistors over planar transistors? We will going to discuss a very detailed manner about all these things in upcoming slides. So observe here planar transistors. So generally CMOS technology is introduced in the planar transistors. So that means combination of NMOS and PMOS. So up to 32 nanometers planar transistors will work perfectly. So if you reduce the process technology from 32 nanometers to 22 nanometers, what may happen means these planar transistors won't work perfectly because of various short channel effects, leakage currents like that. So if the process technology is again reduced to 10 nanometers, 2 nanometers or 3 nanometers, again these three-dimensional transistors, that means FinFETs will not going to work perfectly. So beyond 10 nanometers, what is the best solution? Another three-dimensional transistor is gate-all-around FET. So up to 32 nanometers, planar transistors will work perfectly. If you reduce the process technology from 32 nanometers to 22 nanometers, 21 and 20 nanometers, these planar transistors will have several short channel effects. So due to this we are moving to FinFETs. So that means three-dimensional transistors. So beyond 10 nanometers, these FinFETs will won't work perfectly. Due to the several drawbacks in FinFETs. So beyond 10 nanometer technology, so we are going to move with the gate-all-around FETs. So we will discuss all these things in detailed manner in upcoming slides. So generally these 5 nanometers and 3 nanometer process technologies FinFET experience poor control over leakage currents and faced several short channels. So that's why we are going for gate-all-around FETs. In upcoming slides we will discuss what is planar transistors, what are three-dimensional transistors like FinFETs and gate-all-around FETs. So all these things we will discuss in a very detailed manner. So this is all about our topic. So introduction. So the metal oxide semiconductor field effect transistor, that is MOSFET, may be the most remarkable electronics achievement of the 20th century. The first commercial MOSFET circuits appeared in 1964 and became very popular because of the high packing density, small power consumption and low cost. So it is the structure of MOSFETs which consists of generally 4 terminals: source, gate, drain and pole. Fine. So integrated circuits were introduced in 1958 and complementary metal oxide semiconductor CMOS technology is introduced in 1967. The first commercially produced, that means world's first microprocessor, is the Intel 4004. So it is the world's first microprocessor, commercially, very first commercially available microprocessor released by the Intel Corporation in 1971. So it started a race for miniaturization and performance improvement. So these are the various kinds of integrated circuits in different packages like wheel inline package, quad plate package and ball grid relay like that. So for just reference I had inserted the picture here. See here, Moore's law. So according to Moore's law, a founder of Intel predicted that the number of transistors on a chip doubled every 18 to 24 months. So if you see this particular graph, so in y-axis we will observe the number of transistors, in x-axis we will observe the years. So if you see the transistors count will increase tremendously year by year. So Intel 4004 will have very less number of transistors, but when compared to Pentium 3 and 4 processors, will consist of more transistors when compared to 4004 processor. That means according to Moore's law, the transistor count will increase tremendously every year by year. Okay, so it's all about Moore's law. So we will discuss about the planar transistors. So generally CMOS technology is introduced in the planar transistors. So MOSFETs are the planar devices. So that means these MOSFETs are these planar devices with the metal, oxide and semiconductor involved in their basic structure. So we have two types of planar transistors, that is N-channel MOSFET and P-channel MOSFET. For example, if we consider a planar N-channel MOSFET, for example I am considering, so it is a planar N-channel MOSFET. This planar N-channel MOSFET is formed by diffusing heavily doped N regions. So these are the N plus means heavily doped N regions onto a P substrate. For example, if I want planar P-channel MOSFET, what I will do? I have to diffuse heavily doped P regions onto a N substrate body like that. So over this planar structure, a layer of silicon dioxide is grown. So a layer of silicon dioxide is grown and metallic terminals are etched on the insulating layer of the silicon dioxide. So the metallic layers are in contact with the N regions like this. So we have formed drain to the source. So the gate terminal in the metallic layer on the silicon dioxide with no contact with the N regions. Okay, so these source and drain are contact with N regions. This gate terminal has not contact with this N region. So it's just a simple overview. Simple guys. Planar transistors means CMOS technology is introduced in the planar transistors. What is CMOS means? Combination of PMOS and NMOS. So it is one of the PMOS. Okay. So planar MOSFET. So it's a simple structure which consists of only one gate. Simply. So CMOS technology is introduced in planar transistor which will consist of only one gate. So that's it. So drawbacks of planar transistors. So we have very different kinds of drawbacks are there in planar transistors like short channel effects, variability, quantum tunneling, leakage and mobility degradation. So all these are the drawbacks in planar transistors. That means if you reduce the process technology beyond 32 nanometers, these planar transistors won't work perfectly because of all these drawbacks. Then what's the solution? So the solution is three-dimensional transistor. So that is FinFET. It is one of the three-dimensional transistors. One way of resolving these drawbacks is to introduce a three-dimensional configuration. So that is FinFET. So generally it is a FinFET structure. It is one of the three-dimensional transistor. So FinFET technology introduced one such multi-gate device. It is a multi-gate device, whereas planar transistor is a single-gate device. This FinFET is a multi-gate device, so that utilized fin-shaped FETs. Okay, so it is easy to fabricate multi-gate devices using FinFET technology. So planar construction makes a multi-gate construction is very tedious. Okay. Advantages of FinFET over planar MOSFET. FinFET means, so yes, it is generally a multi-gate device. It uses fin-shaped FETs. That's it. It is one of the three-dimensional transistor we can say. Okay. So advantages of FinFETs means, so short channel effects which are occurring in the planar transistors are overcome by using these FinFETs. So FinFETs are devices with low leakage current. Power consumption is also less when compared to MOSFETs. So the presence of pins gives FinFETs is a better short channel behavior. So FinFET transistors drive strength can be increased by incorporating multiple or longer fins. So FinFETs are high speed devices when compared to planar MOSFETs. So all these are the advantages of FinFET over planar MOSFET. That means, so see here, these are the multi-gate FETs. So generally by using FinFET technology, it is very easy to fabricate multi-gates. But if you use the planar construction of these multi-gate devices is very tedious. See here, it is a triple gate FinFET on a bulk silicon. SI means silicon. So it is a triple gate FinFET on SOI, silicon on insulator. So it is a double gate FinFET on SOI. It is all around gates. That means gate terminal is surrounded, just like a cylindrical type structure here. So it is independent double gate FinFET on SOI. So it is a planar double gate SOI. These are the various kinds of the multi-gate FETs available. So next one. So Intel uses a first three-dimensional tri-grade process for first time. So Intel showed a 22 nanometer wafer at the Intel Developer Forum on September 22, 2009. The size of the cell was the smallest SRAM at that time. So Intel uses a 3D tri-grade processor for the first time. So SRAM by 4. Okay, at the Intel Developer Forum. So drawback of FinFETs. In order to overcome the drawbacks in planar transistor, we come to FinFET now. So then now FinFET also have some drawbacks. So FinFET is also limited, and it has shown the signs of exhaustion in last two generations. At the 3 nanometer process node and beyond, FinFETs may no longer control the leakage current and other charge and effects properly. Okay, so if you reduce the process technology, so beyond 10 nanometers, up to 10 nanometers, these FinFETs will work perfectly. But if you reduce the process technology below 10 nanometers, what will happen? These FinFETs will face several issues like leakage current and other short channel effects. Then now the semiconductor industry and companies face a new transistor revolution. Then what is the new three-dimensional transistor? In order to overcome the drawbacks in FinFET, what we will do? So we will introduce another transistor that is called gate-all-around FET, which is the future of most of the integrated circuits. Okay, so FinFET is a technology with an expiration date. Post FinFET transistor research over the last decade is accessing an evolution from a gate that surrounds three sides of the chip. So if you observe this FinFET structure, this FinFET are having three gates. Planar transistor having only one gate. FinFET having three gates. So that's why FinFET is called multi-gate device. But this gate all around FET will consist of 4 gates. Okay. So gate surrounds three sides of the channel in a gate all around FET. Okay. So this arrangement is a gate all around FET with we have two types: gate all around FET with nano wires and gate all around FET with nano sheets. This design is more involved to build than FinFETs or planar transistors. Nano wires and nano sheets technologies are currently in progress, raising the channel and allowing its width to scale as needed. So that means if you reduce the process technology to 9 nanometers, 5 nanometers, 3 nanometers, this gate all around FET will yields better results when compared to FinFETs. Okay, so it is a structure of gate all around FET. Generally I had said now, we have two types: gate all around FET with nano wires and gate all around FETs with nano sheets. So it is a gate all around FET with nano sheets, which consists of 4 gate terminals. So it is a structure of gate all around FET with nano wires, which also consists of 4 gates. So the first gate all around FET. The first gate all around FET was showcased in 1998 by Toshiba, which was a vertical nanowire gate all around FET. That means this gate all around FET was manufactured by using nanowires. The first gate all around FET uses nanowire is called the surrounding gate transistor. So it is the structure of the first gate all around FET. So gate all around FET is a technology is believed to be the successor to FinFETs, as it provides better device performance at smaller sizes below 7 nanometers. Okay, so in planar transistor we use CMOS technology. In FinFETs we are using FinFET technology. In gate all around transistors we are using gate-all-around FinFET technology, field effect transistor technology. Okay, so it's already I have said gate-all-around FETs are manufactured or fabricated by using nano wires and nano sheets. So the alignment of gate-all-around FET structures can be parallel or perpendicular to the substrate depending upon their implementations. Okay, so MBCFET using gate-all-around transistors. So what is it, MBCFET? Samsung took the first step to position itself as a leader, presenting the multi-bridge. MB means multi-bridge, CFET means channel FET, field effect transistor, at its 3 nanometer manufacturing process. This technology integrates new gate-all-around transistor as the main innovation. That means Samsung introduces 3 nanometer process by using gate-all-around transistors. So see here I had inserted the image. So Samsung introduced the 3 nanometer process with the gate-all-around architecture. That means Samsung replaces the FinFETs by using FinFETs with gate-all-around FETs. So they had manufactured a 3 nanometer process technology by using gate-all-around FETs. So the Samsung highlights some advantages when compared to FinFETs. Those are: no need for an extra area to improve the speeds. Nano sheets are stacked vertically instead of adding parallel pins. Okay, so FinFETs without changing the size or configuration of a device. Okay, we can replace the MBCFETs to able to replace FinFET without changing their size. It can support the same process tools and manufacturing technology as FinFETs. That means no additional tools and separate manufacturing process is not necessary if we use gate-all-around transistors. Okay, so next one is gate-all-around FET advantages over FinFETs. Generally, nanowires or stacked nanosheet technology is employed in gate-all-around FETs, which gives the advantages of raised channel and channel width scalability. There is an easy transition from FinFET to gate-all-around FET fabrication. They reduce costs and allowed manufacturers to quickly implement these new technologies. So when compared to FinFET, in gate-all-around FET we can achieve higher speed. Okay, so all these are the different advantages of gate-all-around FET over FinFETs. So enclosing the channel by the gate in gate-all-around FET, which increases the channel control, which will reduce the leakage currents and brings down the operational voltage and dynamic power. That means if you reduce the process technology to below 3 nanometers, 5 nanometers, we don't face any kinds of short channel effects, leakage currents, mobility degradations, voltage degradations, etc. So all these drawbacks occurred in FinFETs are overcome by this gate-all-around FETs. So why we need different kinds of transistors? We have planar transistors, we have three-dimensional transistors like FinFETs. So, and why we are going for gate-all-around FETs? So why we have to reduce this process technology year by year? That means smartphones. So smartphones and virtual reality or augmented reality. So this IoT. So all these will require ultra low powers, compact size, high speed, high efficiency. For all these reasons, we require better transistors. For compact size, we require less process technology. So for all these requirements, for low power, for compact size, for high speed, for high efficiency, we require better transistors. For better transistors, we are going with the gate-all-around FETs is a better transistor for a future generation. So many substitutes for CMOS transistor are being researched. Adding gates to produce gate-all-around transistors might be the final solution to control electrostatics in ultra-scale channels. In futures, so what are the devices that are manufactured with FinFETs or that means integrated circuits are replaced with gate-all-around FETs to overcome the various drawbacks in FinFETs. Okay, thank you.